Hello and welcome to our discussion on the t-distribution. In this video, we will be reviewing a little bit of what we learned before about the one sample z-test and comparing that to the t-test, so you'll have a comparison there. We'll look at why we use standard deviations instead of sigma, and also how to calculate standard error. Then we will look at why do we use the t-distribution instead of the z-distribution, and the bulk of what we'll be talking about is how that t-distribution is related to z. Because you understand the z-distribution, now you'll be understanding a new distribution called the t-distribution. So as a quick review, we have often when we're doing a study, we have a population, and from that population we take a sample, and as long as that is a simple random sample or some kind of random drawing from the population, then we can make inferences later on about what the population looks like. Now, why do we only look at a sample? The reason usually is that we don't have enough time or money to measure every single person in the population, or it would just take too much time or be too expensive, or we don't have access to everyone. So that's why we take a sample. Once we take a sample, then we measure something, or typically lots of things, and we want to make sure that measurement is accurate in order to know that what it is that we measured is truly a reflection of our sample. And once we have that measurement of things, maybe like means or standard deviations, then we can infer something about our population, like the population mean or the population standard error. Now, when we talked about a z-distribution in the past, when we were learning about confidence intervals and hypothesis testing, what we did is we were basing that on knowing what the population standard deviation was. And so we would have to know that in order to use a z-distribution. Well, in 1908, a gentleman by the name of William Seeley Gossett wrote some interesting statistical papers, and his pen name, he had a good sense of humor, his pen name was Student, and he was working on some industry data, and a lot of times in that industry, their sample size was pretty small. Remember, we have to take a sample of the population, and that sample size really dictates a lot of things. And a lot of times in their particular industry, they would be taking samples of maybe only 3 to 5 N. So they needed to be able to adjust this z-distribution in order for it to behave properly, in order for it to work. And so he wrote in 1908 about what he called the t-distribution. And it is very similar to the z-distribution in a lot of different ways. But as we see, it allows us some flexibility. And so the primary reason that we want to be able to do this is anytime our sample size is less than infinity, then we need to make some kind of an adjustment in order for our results to be correct. So how many times can you think of that we have a study that's done on a sample size that's less than infinity? And I think the answer that you would come up with is pretty much all the time. So we don't always take our whole entire population for reasons we just discussed. And so anytime that sample size is smaller, then we need to make this adjustment to the z-distribution that's called the t-distribution. And this happens when we don't know the population standard deviation, or sigma. Remember, here is we can make inferences about the population, but everything we learned about the z-distribution was dependent on knowing the sigma. And so whenever we don't know sigma, then we need to make this kind of an adjustment, which is usually all the time, because if we knew the mean and standard deviation of the population, then we wouldn't be doing this study. So there are very few situations where we actually do know the population standard deviation, and so this is an adjustment that we need to make pretty much all the time. So that's why t-tests are so popular. So let's do a quick review of the z-distribution. For the 95% confidence interval, that is equal to x bar give or take, plus or minus 1.96 times this sigma over the square root of n. And I know this looks familiar to you. And so we have some kind of measure that's in the middle, this x bar. And then we say above and below that is kind of this margin of error around x bar. And that's 1.96 times our sigma over the square root of n. So therefore, if n is increasing, then that margin of error gets smaller and smaller and smaller. When we don't know sigma, then we have to make this adjustment, and we have to calculate this slightly differently. And so the adjustment looks like this. It looks like the 95% confidence interval is equal to x bar plus or minus, and there's a number instead of 1.96 times, and this is the standard deviation over the square root of n. So notice that we don't have to have sigma because we've replaced it with the sample standard deviation. So the sample standard deviation then in this case is estimating the population standard deviation. And that's a pretty good estimate because we've drawn this simple random sample from our population. And so we're thinking that it's going to be about as spread out as the population that's underlying it. Now, the trick though is that this number right here changes depending on the sample size. And so instead of being plus or minus 1.96 times that, whatever, this is kind of like our measure of standard error, right? This part right here. So here's our standard error when we don't know sigma. Then that is a pretty good estimate of the population. So also, if we think back and we remember about z, this is equal to x bar minus mu sub aught divided by, and here's our standard error again, sigma divided by the square root of n. Now, when we don't know sigma, then instead of calculating z, we calculate t instead. And t looks very similar. T is equal to x bar minus mu sub aught divided by, instead of sigma, we're going to use the standard deviation divided by the square root of n. And so this bottom part, a lot of times people will say the bottom, the denominator of t is adjusted based on the degrees of freedom that we have in that particular study. Now, degrees of freedom are calculated a little bit differently for each type of test that we do, but for a one sample t-test, the degrees of freedom is equal to n minus 1. And that is pretty similar depending on what tests you're looking at, but it depends on how many groups you have. So we'll point that out as we go through our different types of t-tests as we go. So this denominator then is adjusted depending on how many degrees of freedom we have. And if degrees of freedom is n minus 1, then I want to go ahead and start thinking about this question. We're going to play another game of We Never Do This. So let's say you were going to do a particular study. You were going to evaluate some kind of hypothesis. And instead of drawing a sample size of infinity, right here, then we're going to draw a smaller sample size than that. Let's say we're only going to draw a sample size of 1,000. Well, if degrees of freedom, or sorry, not a sample size, we're going to have 1,000 degrees of freedom. If degrees of freedom is n minus 1, then your sample size is 1,001. So do you see how degrees of freedom is 1,001 minus 1? A lot of times you'll see in charts degrees of freedom, and you need to be able to convert back to what is the sample size that they started with. Similarly, if you have degrees of freedom equal to 100, then your sample size was 101. If you have degrees of freedom of 60, then you started with a sample size of 61. Here's 31. Here would be a sample size of 11. Here would be a sample size of 6, sample size of 3, sample size of 2, and so on. And so we're going to show you on a normal curve exactly what those different t-distributions look like. Because remember, I said there's this adjustment that happens because of sample size. And it's because sample size impacts degrees of freedom, and degrees of freedom, degrees of freedom, I don't want to do that. Can we draw? Degrees of freedom impacts, let's go to here. Degrees of freedom then impacts, there we go. Degrees of freedom, I'm getting all kinds of error messages, sorry about that. Degrees of freedom impacts the denominator. So that's the relationship then between sample size and this t that we're talking about. Now, quick reminder before we go into exactly what the t distribution looks like on a normal curve. We've said that sample size is one of the reasons that we need to make these adjustments. And remember, sample size impacts all kinds of things. Sample size has to do with the central limit theorem, specifically that the sampling distribution of the mean has a shape that is normal when we get a larger and larger sample size. So there's the whole normality issue. Due to the square root law, the standard error tends to get narrower and narrower as our sample size goes up. According to the law of large numbers, the location of x bar gets closer and closer to the actual population mean as our sample size goes up. When we talked about estimation, our 95% confidence interval gets narrower and narrower the larger the sample size gets. And I want to add one more thing to this. When we have a larger and larger sample size, then our t actually starts approximating what the z distribution looks like. So as our sample size goes up, then the t distribution starts looking more and more and more like the z distribution. And you're going to see that over here when we do our play the rest of our game, the We Never Do This game. So let's look first at some of the similarities between the z distribution and the t distribution. In terms of the z distribution, remember it was bell-shaped and symmetrical. So it has this nice normal curve. It's bell-shaped and symmetrical. And so that's the same. Bell, the location for both is at the population mean, and the spread is dictated by what the sample size is. So remember this sigma is constant and fixed, and so we end up with a spread that is very consistent, whereas the sample standard deviation right here is measured with error, and so that dictates how far things are spread out. So that is one of the important differences, is that depending on the sample size, the shape has a lower peak, the t distribution has a lower peak, and it can be more spread out. In other words, what we call heavier tails. And so if what I have drawn here in red, and then I kind of traced it in blue, is the z distribution, if I draw something in green where the tails are actually maybe a little bit more spread out and the peak is a little bit lower, then that would signify that the peak is a little bit lower, and there's more here in the tails. There's more weight in the tails. I want to undo that little scribble that I made. And then as my sample size gets smaller and smaller and smaller, then I'll draw another one that has even heavier tails and even a lower peak. And so you see that it squashes, by having a smaller and smaller sample size, it actually squashes that normal curve down so that it's still bell-shaped and symmetrical, and still the middle of it is located in the same place as the z-distribution, but the tails become heavier and heavier as your sample size gets smaller and smaller. And so let me put some numbers to this that I think will be helpful. Let's remember that for the z-distribution, if we think of what is the area, and I'm going to draw this just inside of that 2.0 mark to remind us that it's a little bit shy of 2. The z-distribution that captures, and I'm just going to draw here, that captures 95% of this area under the curve. Let me see if I can draw it in red right here. The z value that we need in order to capture that 95% is equal to 1.96. So this is negative 1.96 and this is positive 1.96. And so that is the location where this cutoff happens, where 95% of the area under that curve is actually captured. So give or take 1.96, and remember over here, here's our 1.96. So give or take 1.96 times that standard error gives us that 95% confidence interval. Now a t-distribution, on the other hand, when I have 1,001 sample size, so I have 1,000 degrees of freedom, the t that I need in order to capture that same 95% confidence, that same 95% of the area under the curve, is equal to negative 1.962 and positive 1.962. And so now I've just made this confidence interval a teensy bit wider in both sides, and so I'm drawing a tiny little arrow there. Let's look at a sample size of 101, or degrees of freedom of 100, and the t-value now that I need in order to capture this same 95% of the area under the curve is now going to be negative 1.984 to positive 1.984, and hopefully you'll see that that has spread even a little bit farther in that direction. Those arrows are not to scale, by the way. If I have a sample size of 61, and I like 61, it is a prime number, that gives us 60 degrees of freedom, and this is the point where that z-value, or not z-value, but the t-value that captures 95% of the confidence or of the area under the curve is exactly equal to 2.000. So negative 2 to positive 2. So you can remember sample size of about approximately 60 or 61 is where you would have, for this t-value right here, here's your 95% confidence interval, this would be exactly a 2.0. And that's sort of the estimate that we've been using instead of calculating it at 1.96 as an estimate. As your sample size keeps getting smaller and smaller and smaller, remember we never do this. We don't run a study over and over and over again and take one sample of 1,001, a different sample of 101, a different sample of 11. We don't do that. But this is just to model what if we did. So if we have a sample size of 31, so 30 degrees of freedom, that now is 2.042. So plus or minus 2.042. And so you can see that this is getting wider and wider, because as the sample size gets smaller and smaller, it pushes this peak down. It pushes more of the area into the tails, and so we need to go wider and wider and wider and wider in order to still include that 95% of the area under the curve. What if we only have a sample size of 11? Then we have a t-value of 2.228. in order to capture that 95%. So here we have 2.228. What about a sample size of 6? And so we have degrees of freedom equal to 5. We have a negative 2.5. 7, 1 to positive 2.571. So all of a sudden we're actually out here. We're getting quite a bit wider and wider as our sample size gets smaller and smaller. What if we only have a sample size of 3? So we have 2 degrees of freedom. Hopefully you'll see that this is progressing quite a bit now. The t-value that we would need to go to, because so much of this area has been pushed into the tails because we keep pushing the peak down, this has now become a 4 point, I don't even have enough room to go that far out on this particular graph, 4.303. And so this is a negative 4.303 to positive 4.303. And this is kind of some of the sample sizes that this William Seeley Gossett, they were sometimes collecting only 3 or 4 samples, and then they said, yeah, we need to be adjusting this. We can't use this plus and minus 1.96 anymore. We need to adjust that in order to come up with the right answer. What if you only have a sample size of 2? That number becomes 12.71. I hope you can appreciate negative 12 to positive 12 is quite a bit wider. A lot of that area has been pushed now into the tails. So in order to capture that 95% confidence, we would need to use a different number, and that different number happens right here. When we're looking at that 95% confidence interval, it is dependent on the sample size, basically, and we use whatever that t-value. So remember when we were doing the z, as soon as we calculated z, then we converted that to a p-value. The same thing happens with t, and that conversion of t depends on the standard deviation and the sample size. And so we convert this to a p-value. And that distribution, you saw we kind of drew several of these distributions, and some of them had even heavier and heavier tails depending on, and this obviously an exaggeration because it doesn't level out like that. But so T is a family or a collection of different distributions. This T distribution is a collection of different kinds of curves, and it completely depends on the sample size. So as the sample size gets larger and larger and larger, then T starts to approximate the Z distribution. It gets closer and closer and closer. And the smaller and smaller and smaller the sample size, the more and more different from Z these values become. And so I hope that is a good overview of the difference between the Z distribution and the T distribution, so that you have a pretty good sense of how that T distribution is related to Z. Also, remember that you're going to need to know how to calculate standard error. Here's how we calculated it when we knew sigma. Here's our new way to calculate standard error. Now that we aren't dependent on sigma, we use the standard deviation divided by the square root of n. Why we use t instead of z, and it's because there needs to be this adjustment factor. And then finally, why standard deviation instead of sigma, and that is because we don't know sigma. Sigma is a mystery. We don't always have that population parameter. Thank you for joining me, and we'll see you in the next video.